We all take gravity for granted. Yes, it's one of the four fundamental forces of nature that keeps our feet on the ground and makes sure Earth is orbiting the sun. It's something we feel every day, making it seem quite intuitive. Whatever goes up will fall down. But the more you dig into it, the more you realize there's a whole lot more to this force than meets the eye. Today, we'll look beyond the classic Newton-apple tale and uncover 5 intriguing facts about gravity that are often misunderstood, oversimplified, or still puzzling to many. 5. Gravity is not exactly a force. The 4 fundamental forces of nature, strong and weak nuclear forces, electromagnetism, and gravity, are often considered to be the underlying explanations for all interactions in the universe. However, some physicists prefer to refer to these as the 4 fundamental interactions, as gravity doesn't quite fit the same mold as the other 3. To understand why, let's take a step back and explore the concept of gravity. For over 2 centuries, our understanding of gravity was based on Sir Isaac Newton's groundbreaking work, which described the attraction between 2 objects as an equal and opposite force that can be calculated based on their masses and relative distance. According to Newton's theory, the Earth's gravity pulls you towards its center, and you, in turn, exert a gravitational force on the Earth, albeit a much weaker one due to your smaller mass. Newton's model was incredibly successful, easy to understand, and experimentally confirmed. However, even Newton himself was puzzled by one aspect of his theory. He couldn't explain what caused gravity or how it managed to act over vast distances without any medium. In a letter to Richard Bentley, he expressed his skepticism, writing that the idea of one body influencing another across a vacuum without any intervening mechanism was so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Imagine the collective sigh of relief from scientists worldwide when Albert Einstein finally cracked the code on gravity with his groundbreaking theory of general relativity. For centuries, gravity had been viewed as a force that acted between 2 objects, but Einstein turned this notion on its head. He revealed that gravity isn't a force at all, but rather a byproduct of mass distorting space-time. You might recall learning in physics class that an object in motion stays in motion unless acted upon by an external force. This means that if you're cruising through the vacuum of space, your speed and direction would remain unchanged until something intervenes. Newton's laws of motion were spot on, and Einstein built upon this foundation to revolutionize our understanding of gravity. In a Newtonian model, your path through space would be a straight line, bent by gravitational attraction, curving your trajectory towards the object. But Einstein showed that it's not your path that's curved, but rather space itself. This distinction may seem subtle, but it's crucial. Mass warps and stretches space-time, making what we perceive as a straight path actually curved along this warped terrain. This curved yet straight path is called a geodesic. For context, let's consider commercial air travel. Pilots aim to take the shortest route to their destination, which appears as a straight line from their perspective. However, when you zoom out, you see that their overall path is curved, following the Earth's surface, which curves into a third dimension on a spherical surface. Similarly, objects travel in a straight line guided by the curves of space-time, giving the illusion of a mysterious force pulling a planet towards a star. But in reality, there's no force, no invisible push or pull, just the star's mass warping space-time. Think of it like this. Gravity feels strongest where space-time is most curved, and it vanishes where space-time is flat. This is often summed up in the words of John Archibald Wheeler as follows: "Matter tells space-time how to curve, and curved space-time tells matter how to move." 4. Our theories fall apart at the quantum level. Thanks to general relativity, we now have a more accurate model of gravity, refining the insights originally provided by Newton. However, it is not without its limitations. One significant issue is that gravity remains the only fundamental interaction that has yet to be reconciled with quantum mechanics. In essence, relativity describes larger objects, while quantum mechanics describes the universe at a subatomic level. Typically, when working with the domain of one, the other can be safely ignored, as they describe different aspects of the universe. However, there are situations where both are necessary to fully understand what is occurring, such as during the moments immediately following the Big Bang or near the singularity of a black hole. To achieve a complete understanding of the universe, these two theories must eventually find common ground. This has led to a decades-long search for a theory of quantum gravity, or a theory of everything, that unifies all domains, including gravity. Over the years, various models have been proposed, such as loop quantum gravity, M-theory, string theory, and twistor theory, among others. One challenge shared by these theories is that they predict results at extremely high energy levels or tiny regions of space, making them nearly impossible to verify with real-world experiments using current technology. For instance, loop quantum gravity predicts that space-time is not continuous, but rather composed of distinct pieces or bits that cannot be divided further. This theory also makes up the surprising prediction that the speed of light is not constant, but varies slightly depending on a photon's wavelength. However, the difference is so minuscule that it is currently undetectable. Similarly, several predictions made by string theory require energy levels that are beyond the capabilities of current particle accelerators. While these theories have contributed interesting scientific and mathematical insights, they lack experimental validity and therefore cannot be solidified as accepted science. As a result, there is no consensus in the scientific community regarding quantum gravity, and the field is actively developing. It is an area worth monitoring in the coming decades, as fresh ideas and technological advancements may enable us to experimentally verify these theories and finally reconcile gravity with quantum mechanics. 3. Gravity is limited by the speed of light. In physics, few equations have made a bigger impact than E equals mc squared, showing the relationship between energy and mass. However, the significance of this equation extends far beyond its mathematical simplicity. However, the speed of light denoted by the letter c is not just a constant specific to light, but rather the universal speed limit that governs the movement of all objects, including light, massless particles, and even information. Albert Einstein's groundbreaking theory of relativity not only unveiled the connection between energy and mass, but also predicted the existence of gravitational waves. These ripples in space-time, born from the fabric of gravity, propagate at the speed of light, carrying information about the universe's most violent events. The implications of this discovery were profound, suggesting that even the most massive objects, such as stars and black holes, could be connected through a web of gravitational waves. But there was a catch. Detecting these waves was deemed nearly impossible, as they would be minuscule and tough to measure. For over a century, scientists doubted whether the technology would ever advance enough to capture these elusive signals. That was until the development of the Laser Interferometer Gravitational Wave Observatory, LIGO. LIGO is an intricate instrument comprising two L-shaped tunnels, each approximately 2.5 miles long, equipped with a sophisticated array of lasers and mirrors. The concept is ingenious. If a gravitational wave of sufficient strength were to pass through the system, it would create a brief, imperceptible distortion in the length of the tunnels. This distortion would in turn affect the timing of the laser beams, causing them to recombine imperfectly and produce a detectable signal. In reality, the process is far more complex, as scientists must account for background interference from various sources, including the Earth and the Sun. However, the basic principle remains the same. On September 14, 2015, after a series of upgrades, LIGO's detectors finally picked up the faint signal of a gravitational wave, which was heralded by a brief, audible chirp. This momentous discovery not only earned several scientists the Nobel Prize in Physics, but also vindicated Einstein's century-old prediction. To pinpoint the origin of the gravitational wave, a collaborative effort was launched across the astronomical community. By combining LIGO's findings with sky surveys and gamma-ray detections, researchers were able to narrow down the search area. The fact that the waves were detected by two separate LIGO systems located in Washington and Louisiana provided a crucial clue. The 7-millisecond delay between the two sites indicated the general direction of the source, leading scientists to conclude that the waves originated from the merger of two binary black holes, each with a mass approximately 30 times that of our Sun. This cataclysmic event, which likely occurred about 1 billion light-years away in the direction of the Magellanic Clouds, would have taken place long before the emergence of vertebrates on Earth. 2. Gravity is most intense in black holes. The Einstein field equations, formulated in 1915, describe the geometry of space-time within the framework of general relativity. Shortly after their publication, Carl Schwarzschild found a strange solution suggesting a point in space where, under extreme density, some terms in the equations become infinite. We now refer to this as a singularity, surrounded by a gravitational field so intense that not even light can escape, creating what we know as a black hole. Although entire libraries could be filled with books on black hole singularities, let's explore a few lesser-known aspects of black holes. Contrary to the common belief that black holes act like cosmic vacuum cleaners, sucking in everything around them, this is a misconception. If you remain outside the event horizon, the boundary beyond which return is impossible, a black hole's gravitational pull is no different from any other object of the same mass. For instance, if the Sun were replaced by a black hole of equal mass, the planets would continue their orbits unchanged, without being drawn into the black hole. Moreover, even light can orbit a black hole. At a certain distance from the black hole, known as the photon sphere, light is trapped in a perfectly circular orbit, maintaining a delicate balance between falling into the black hole and escaping into space. This phenomena gives rise to intriguing scenarios, such as standing in a spot where light reflecting off your head travels around the black hole and back to your eyes, enabling you to see the back of your own head. If, in the course of setting up such an experiment, you accidentally fell past the event horizon, the reality of no return would become starkly clear. Each celestial object has an escape velocity, the speed needed to break free from its gravitational pull. For Earth, this is about 25,000 miles per hour, while for the Sun, it's around 1.4 million miles per hour. However, within a black hole's event horizon, the escape velocity exceeds the speed of light, rendering escape impossible. Beyond the mere inability to achieve sufficient speed, crossing the event horizon means encountering an extreme warping of space-time. This distortion is so profound that all paths inevitably lead to the singularity, not just in space but also in time. Space-time's curvature becomes so severe that your timeline has a definitive endpoint at the singularity. Regardless of your direction or speed, every conceivable path through space-time converges on the singularity, driven by the relentless force of gravity. 1. Gravity warps the passage of time. Einstein's predictions about time dilation are quite remarkable, and there are two main types, one related to velocity and the other to gravity. Let's delve into the latter, which is known as gravitational time dilation. This concept can be mind-bending, but we'll simplify it for you. According to relativity, the proximity of an observer to a massive object affects the passage of time. The closer you are to a gravitational source, the slower time passes relative to someone farther away. This means that, in principle, someone living on the surface of the Earth would experience time passing slightly slower than someone living on the Moon, due to the stronger gravitational pull. However, when it comes to objects like the Earth, the difference is incredibly small, a tiny fraction of a second over a human lifetime. It's worth noting that the strength of gravity is significantly greater at the Earth's core, which means that if you were to start clocks at the moment the Earth formed, you'd find that the core is about 2.5 years younger than the surface. The movie Interstellar brilliantly showcases gravitational time dilation. On Miller's planet, an hour is equivalent to 7 years on Earth, because it is so close to a massive black hole. This phenomena is why the main protagonist ends up younger than his own daughter by the film's end. Confirming time dilation experimentally was limited only by the precision of clocks, which improved dramatically throughout the 20th century, leading to multiple confirmations of Einstein's theories. Even simple experiments such as placing atomic clocks at different altitudes yielded the expected results, showing that time passage is influenced by the strength of the gravitational field. To gain a deeper understanding of why this occurs, it's essential to remember that time is intricately linked to spacetime, according to Einstein. When a massive object warps space-time, it also distorts time, causing the difference in time passage. Think of time as a linear journey, where each milestone marks a year past. When you're in a strong gravitational field, like near a black hole, the distance between each milestone increases, making it take longer to reach each year. This means that time passes more slowly for the twin near the black hole compared to the twin on Earth. The fundamental point of relativity is that each observer experiences time as passing normally, and time dilation only becomes apparent when comparing two different locations.
Normally, a gifted soccer player on Earth can get off the ground, jumping with feet together, by at least half a meter. But how would this go on all the other objects in the solar system? How far would he be able to jump? A ball thrown 30 meters high here on Earth returns to the ground after just 2.5 seconds. But on Mars, on Jupiter, on Phobos? Let's try to find out by reviewing all the classic planets of the solar system, plus a few objects with more extreme characteristics. Gravity on Mercury. With a mean diameter of about 4,888 kilometers, Mercury is approximately one-third the size of Earth and about 18 times less massive than Earth. This makes Mercury the smallest and least massive planet in the solar system. However, thanks to its high density, a robust 5.43 grams per cubic centimeter, which is just slightly lower than Earth's 5.5 grams per cubic centimeter, Mercury has a surface gravity of 3.7 meters per second squared, which is the equivalent of 0.38 g. Okay, if we played soccer on Mercury, a soccer player jumping to hit the ball head-on would be 1.3 meters off the surface, while players on the field would have to wait 4 seconds for the ball to become playable again after a 30-meter flight. Gravity on Venus. Venus is similar to Earth in many ways, which is why it is often referred to as Earth's twin. With a diameter of 12,200 kilometers, a mass that is 0.815 times that of Earth's, and roughly 0.95 times as dense, it's no surprise why the gravity on Venus is very close to that of Earth's 0.9 g, or 8.9 meters per second squared. Thus, we should also not be surprised that a soccer game on Venus would be played under almost the same conditions as on Earth. A soccer player would jump 0.6 meters and the ball would take 2.6 seconds to return to the ground. Gravity on the Moon. This is an astronomical body where humans have experienced firsthand the effects of decreased gravity. Based on the average diameter of 3,474 kilometers, mass 81 times smaller than Earth's, and density of 3.3 Gs per cubic centimeter, the Moon's surface gravity has been measured to be 1.62 meters per second squared, or 0.165 G. Applying the formulas we discussed earlier, from this data we get that a soccer player would be able to jump onto the Moon to a height of 2.7 meters, and the players on the field would have to wait 6 seconds before the ball would descend again from a height of 30 meters. Gravity on Mars. Mars is also similar to Earth in many key respects. However, when it comes to size, mass, and density, Mars is comparatively small. In fact, its mean diameter of 6,678 kilometers is the equivalent of roughly 0.53 Earths, while its mass is just 0.107 Earths. Its density comes in at a relatively modest 3.9 G per centimeter cube. Because of this, Mars has 0.38 times the gravity of Earth, which works out to be 3.7 meters per second squared. It might be surprising to see that despite Mars being twice as massive as Mercury, the gravitational pull at the surface of the two planets is actually the same, 0.38 G. This indicates that Mercury is much denser than Mars, and therefore its surface is closer to its center of mass than Mars is. And as we saw earlier, gravity is stronger when the distance between two masses is smaller. As for the soccer game, a player on Mars would therefore jump the same size jumped on Mercury, or 1.3 meters, and the ball would also take the same time of 4 seconds to descend to the ground. Gravity on Jupiter. Jupiter is the largest and most massive planet in the solar system. Its mean diameter at 140,000 kilometers makes it 11 times the size of Earth, while its mass is the equivalent of 318 Earths. But being a gas giant, Jupiter is naturally less dense than Earth and other terrestrial planets, with a mean density of 1.33 g per centimeter cubed. What's more, being a gas giant, Jupiter does not have a true surface. If one were to stand on it, they would simply sink until they eventually arrived at its theorized solid core. As a result, Jupiter's surface gravity, which is defined as the force of gravity at its cloud tops, is 24.8 meters per second squared, or 2.5 g. Imagine playing a game on a space platform. A soccer player would barely be able to get 0.2 meters off the ground, and the ball would only take 1.5 seconds to descend from a height of 30 meters. Even in the case of Jupiter, the low density and thus the distance of the surface from the planet's center of mass greatly scales down the effects of a mass that would suggest a much stronger gravity. Gravity on Saturn. Like Jupiter, Saturn is a huge gas giant that is significantly larger and more massive than Earth, but far less dense. In short, its mean radius is 116,500 kilometers. Its mass is 95 times as massive and has a density of 0.7 g per centimeter cubed. As a result, its surface gravity, again measured from the top of its clouds, is just slightly more than Earth's, 10.4 meters per second squared, or 1.07 g. One would think that such a large and massive planet should have a very high gravity at the surface, but for the reasons already stated, the hypothetical soccer game played at the top of its clouds would be played almost as well as on Earth. A soccer player would come off to a height of 0.4 meters, and the ball would return to the ground in 2.4 seconds. Gravity on Uranus. With a mean diameter of 50,700 kilometers, Uranus is approximately 4 times the size of Earth and 14.5 times as massive. However, as a gas giant, its density, 1.27 g per centimeter cubed, is significantly lower than Earth's, hence why its surface gravity, measured from its cloud tops, is slightly weaker than Earth's, 8.7 meters per second squared, or 0.9 g. Again, despite its size, there is not much difference with Earth's gravity. A soccer player would be able to jump 0.6 meters and the ball would fall back to the ground in just over 2 seconds. Gravity on Neptune. With a mean radius of 49,000 kilometers, Neptune is the 4th largest planet in the solar system. All told, it's 4 times the size of Earth and 17 times as massive. But being a gas giant, it has a low density of 1.6 g per centimeter cubed. All of this works out to a surface gravity of 11 meters per second squared, or 1.14 g, which again is measured at Neptune's cloud tops. In short, on the last planet in the solar system, a soccer game would turn out to be quite smooth, with players coming off the ground by 0.4 meters and balls taking 2.3 seconds to descend from a height of 30 meters. Gravity on Ceres. The dwarf planet, king of the asteroid belt, has an average diameter of 940 kilometers and a mass that is only 6,000ths of Earth. Its surface gravity is just 0.27 meters per second squared, which would allow a football to come off the ground to a height of as much as 16 meters. In contrast, the ball falling from a height of 30 meters would take 15 seconds to descend again. Imagine how a game might unfold, where players kick the ball and then stand with their noses up to wait for its return. Gravity on Phobos. The larger of the 2 Martian moons is nevertheless very small. In fact, it possesses an average diameter of only 22.5 kilometers and a virtually insignificant mass. Its surface gravity, as a result, averages just 0.0057 meters per second squared, so that a soccer player could rise by jumping feet first to a height of 88 meters, and the return of the ball to the ground would have to wait for 102 seconds, almost 2 minutes. With the danger then of dozens of balls being lost in space during the game, the escape velocity from Phobos being only 41 kilometers per hour, a speed that a soccer ball tossed from one side of the field to the other could easily overcome. And on the Sun, we almost forgot about the host. The Sun has a huge diameter of almost 1.4 million kilometers and a mass that is 333,000 times that of the Earth. The density is not much, but still the force of gravity measured on the photosphere is 274 meters per second squared. Playing a game on our star would mean having players jumping less than a couple of inches and balls coming back down in as little as 0.5 seconds. All in all, gravity runs the gamut here in the solar system, ranging from 0.38 G on Mercury and Mars to a powerful 2.53 G atop Jupiter's clouds. And on the Moon, where astronauts have ventured, it is a very mild 0.165 G, which allowed for some fun experiments in near weightlessness. Understanding the effect of zero gravity on the human body has been essential to space travel, especially where long-duration missions in orbit and to the International Space Station have been concerned. In the coming decades, knowing how to simulate it will come in handy when we start sending astronauts on deep space missions. And of course, knowing just how strong it is on other planets will be essential to manned missions and perhaps even settlement there. Given that humanity evolved in a 1G environment, knowing how we will fare on planets that have only a fraction of the gravity could mean the difference between life and death.